Hello folks, Mr. Dooley here. I'm going to walk you through worksheet number 7, and what we're doing here is we're going to combine the last two lessons together. So 2 lessons ago, Mr. Murphy showed you guys how sigma notation works, and then the last lesson, Mr. Scott showed you how the formulas for series works. And so what we're going to do is we are going to take a series, like in this one in number 1, and we're going to write it in sigma notation. So we got to write this in sigma notation, okay? And then the second part of this is then we're going to evaluate it. What would be the sum of this? And we'll use that using the sum formula. So writing it in sigma notation is building on what Mr. Murphy taught you guys. And then part 2, evaluating the sum using the sum formula. That's what Mr. Scott showed you. So let's start by trying to figure out what type of series this is. Is this an arithmetic series or is this a geometric series? Well, it's pretty obvious that it's arithmetic and that the difference is 3. So let's write a few things down. Let's write down that we know that the difference is 3. We know it's arithmetic. We know that T1 is 5. You know, we don't know how many terms are in here, which we do need to know. This is unknown. We know that we're stopping at 65, but we don't know what term 65 is. Tn is 65. What is the value of n? So in order to figure that out, we need to go back to our formulas for finding specific terms. And what we'll do is this represents Tn, and it's 5 plus the difference 3 times n minus 1. So this is coming from our formula of Tn equals T1 plus d times n minus 1. That's where this is coming from. Okay? And so what you're going to do is you're going to solve this. I'll skip over that part, but it's pretty easy to solve. It's just a simple algebraic expression. And what you end up with is n is equal to 25. So within here, n equals, I didn't mean to say 25. I said 25. I didn't mean to say 25. I meant to say 21. And so the value of n is now, let's write this in red. Oh, how about we try a pen rather than a value of n is 21. Okay. So writing this in sigma notation. Well, start off by writing the sigma, capital letter sigma, Greek letter. And we know that we're going from the first term to the 21st term. This is T1, this is T21. So we're going to go from n equals 1 to 21. Now, what goes here? Actually, this goes here, because this is the formula for finding a specific term in this particular series. And so that's what we pop right in there. We pop 5 plus 3 times n minus 1. Now, I'm going to clean that up, and that's how we're going to write this in sigma notation. So n equals 1 to 21. And when you clean this up, you end up with 3n plus 2. So that's part 1. That's how you take a series and you write it in sigma notation. A couple of things you may see in the textbook and in other worksheets that rather than n is replaced with the letter k. Certainly, you could do that if you felt like you wanted to make this k's. You could certainly make these k's. K's goes from 1 and just make that k like that. You could definitely do that if you wanted to. I'm sticking with the n. That's just the way that I roll. So that's how I'm doing that. Part 2. Part 2 says use the appropriate sum formula in order to find the sum. Well, since this is an arithmetic, we would use the arithmetic sum formula, partial sum. And what you do is you take the first term, which is 5. You add it to the last term, which is 65. And then you times that by the number of terms, which is 21 over 2. And this will give you the sum of the series, which is 70 times 21 over 2, which is 35 times 21. 35 times 21 is 735. Some of you with a newer calculator, you can actually do summation notation on your calculator. I believe the newer ones, I believe it's under math, the math key. And so you could check your answer with that if you felt strongly about it. So this is part 1, writing it in sigma notation. This is part 1 right here. And then finding the sum, finding the actual sum, evaluating the sum is number 2 right there. So our second problem is right here. And you can see we're dealing with fractions. We're dealing also, we've got alternating between positive and negative. That's a clear indication that this is geometric. And you could see down here, right, this is times by 5, times by 5. And since it's alternating, and since this is in the denominator, we could tell that our ratio, our common ratio, is negative 1/5. This is certainly geometric. Now, just like in example number 1, we need to write down what the first term is, which is 1/2. And we also need to know how many terms there are. Now, listen, let's be smart about this, right? So this is a geometric series. And geometric gets very large very quickly, right? So this denominator of 31,250, it may seem really large, but it's actually not that many terms away because you're continually timesing by 5. So like 50 times 5, right, is 250. That would be the fourth term. The fourth term would be negative 1 over 250. The fifth term is 250 times 5, right? Which gives you 1,250. So we're already into the thousands. You can just do a little check on your calculator, and you'll find that 31,250, it would be the 7th term. You could do this using the geometric formula and doing logs, and not necessary in this problem. Just it'd be more efficient if you just take your calculator and keep timesing by 5 and count, and you get up to the 7th term, and there it is. So once we have this, we can write this in sigma notation, and we're going from the first term to the 7th term. And in here, what we're going to put is we're going to put in the formula for finding a geometric term, right? So for geometric, it was T1 times R to the n minus 1. So we've got 1/2 times, ratio is negative 1/5, raised to the n minus 1 power. Let's get rid of that circle there, oval here. Yeah. There you go. There it is in G. That's our sigma notation. N goes from 1 to 7, and then this is the formula for finding a specific term. Now, you could, if you wanted to get into the nitty-gritty of this, you could simplify 1/2 times negative 1/5 to the n minus 1, but it's not necessary for us to do that. So we're just going to leave it just like this. This is part number 1. And part number 2 is to actually evaluate the sum. So for this, we need to use our formula for finding a sum for a geometric series. And Mr. Scott showed you yesterday that that formula is T1 times 1 minus R to the n over 1 minus R. And so putting in those values, we can find the sum of the first 7 terms would be 1/2 times 1 minus negative 1/5 to the 7th power all over 1 minus negative 1/5. Okay, so you bang this out, and you get 0.416672. I have an older calculator, so maybe the newer calculators might convert that nicely to a decimal, to a fraction. But that's what I got. You could do it by hand and get a fraction, what you would get as a fraction, you get this insane looking fraction. But decimal answer in this is perfectly fine. So why don't you guys take a moment and you guys try number 3 and pause the video and come back and you can check out your answer and see if it's correct. There you go. Arithmetic. Difference is 1. Sigma notation here. Sum here. All right, flip it over to the next page and we'll get started on that. All right, so now in this particular problem, we are given 2 terms in a geometric series. So they're giving to us that this is geometric, and they're giving us 2 terms. They're giving us the 3rd term and they're giving us the 5th term, and we need to write the partial sum of the first 10 terms using sigma notation. So this is a challenging problem, and so the way that I'm going to do it is I'm going to do it this way. Okay. So this is my first term. I don't know what it is. This is my second term. I don't know what it is. My third term is 1. My fourth term, don't know what it is. And then my fifth term, I do know is 4/9. And this is going to go all the way out to my 10th term. And the reason why is because we want to find the partial sum of the first 10 terms. So in order to do this, we need to figure out what T1 is, and we need to figure out what the ratio is. We know that n is 10. We don't know what T1 is, and we don't know what the ratio is. Those are what we need in order to figure out how to write this in sigma notation. So since we know that this is a geometric series, I know that to get from 1 to 4/9, I need to times by r and then by r again. So 1 times r squared is equal to 4/9. This is a quadratic equation, and this is very easily solvable. R would equal plus or minus 2/3. So we actually have 2 possible values for r, and that was put in this note up here. Remember, there are 2 possible values for r. So we need to write this. We're going to end up writing this as 2 possible answers. So one of these r's, right? Now that we know this, r would be 2/3 or negative 2/3, right? You could write it just as a plus or minus. Well, we also need to know what T1 is. So we just have to backtrack. So what we're going to do is we're going to go backwards twice. So we're going to divide by 2/3. So we're going to do 1 divided by 2/3, and that gives me 3/2. And then we're going to do 3/2 divided by 2/3, and that gives me 9/4. And that would be if R was 2/3. So T1 now is 9/4. Let's put that in black. If T was positive 2/3, and actually T1 would be 9/4 even if R was negative 2/3, because if it was negative 2/3, T2 would be the value that was negative, and then T1 would then be positive again. All right, so I have my information. I have enough information to write my sum in sigma notation. So let's do it. We're going from 1 to 10. 9/4 T1 times my ratio, which is 2/3 to the n minus 1 power. And if we were to do this with negative 2/3, it would be this same exact sigma notation with one quick change, which would be making that negative 2/3. Okay? And now for the sums, for this one, right, we use that sum formula. And for this one, we use the sum formula. So why don't you guys, I'm going to pause this, or you guys pause this, do the sums, come back, and you'll see the answers. There you go. All right. Last problem on today's lesson is a problem that you've actually seen before, where you are finding geometric means. If you're finding the value of R in a geometric series, you are finding geometric means. So in this problem, what we have is right, T7 is 4. This is right. This is T7, T8, T9, T10, T11, and this is 4, this is unknown, this is unknown, this is unknown, and then this is 0.0004. And so what we're trying to figure out is what would be the value of R, and in this problem, we are going to be allowing R to be complex. So you could see that in order to get from the 7th term to the 11th term, you are timesing by R 4 times in a row. That means 4 times R to the 4th would be 0.0004. Now, this is a quartic. Quartic have 4 solutions, 4 roots. And if you work this out, you will find that R, right, R to the 4th, you divide by 4, is 0.0001. That is 1 over 10,000. And that gives us these values. R would be plus or minus 1/10, and R would be plus or minus 1/10 I. Now, to find T8, T9, T10, take each of these, and you've seen this a few lessons ago, and I think Mr. McGivney did this. And so take each of these 4 values of r, and you can just fill in this little chart using those values of r. Those lines represent T8, T9, and T10. So this would be T8, T9, and T10. So take a moment. You could use your calculator and multiply these out and get those values, and I'll pop them in while you do it on your own. You can see that I used fractions, but you could, because it was just easier to do since you're just timesing by 4 times 1/10 each time. So you're just timesing the denominator by 10 each time. So it was easier for me to do it as a fraction. But if you were doing decimals, you know, those would be 0.4, 0.04, 0.004. So you get the idea. Okay. And lastly, they're giving us the sum, and we want to know how many terms went into finding that sum. Okay, now, if you remember, for a geometric sequence, that is the sum formula for a geometric series. And we are using, it says, the positive real value of n. The positive real value of n. That means the positive real value of r. That means that r would be 1/10. That would be my positive real value. I do know that n is unknown, right? We don't know what that is. We do know that the sum is 4,444,444. We don't know what T1 is, but we can very easily figure out what T1 is just by backtracking and timesing by 10. So T7, for example, is 4. And so we would be timesing by 10. So T6 would be 40, and T5 would be 400, and T4 would be 4,000, etc. So 3 would have 4 zeros, 2 would have 5 zeros, and 1 would have 6 zeros. So we know that this would be a 4 with 6 zeros, 4 million, times 1 minus 1/10, why don't we write it as 0.1 to the nth, over 1 minus 0.1. So we just have to solve this. Let me erase this stuff here. We don't need this anymore. So we just have to solve this. And 1 minus 0.1 is 0.9. So we're going to times this by 0.9. That gets rid of that. And then we would divide by 4 million. And you get a bunch of 9s here. 7 9s. We're going to minus 1. And then the negatives will cancel. So we're going to get 0.2, 3, 4, 5, 6 with a 1 equals 0.1 to the n. And then the you could do a natural log. You could do a log 0.1, a 0.000001 equals, and that will give us our n value. 8 n equals 7. Reality is that once you knew that T1 was 4 million, you knew that the sum, since the sum that we were looking for was 4 million, it would go up to, you know, however many decimal places there are. So you could have easily guessed, you know, that it would just go up to the 7 because up to the 7th term, because after the 7th term is all decimals, and that sum is a whole number. And so you could have easily guessed that that was 7 if you wanted to do it that way. But there's the math. So you have an exit slip that is similar to some similar questions to these. Good luck.